Just like we have a place to live in the world of subatomic particles, electrons have their own place where they go, and it is dictated by electronic configuration. Or we can say that the distribution of electrons into orbitals of an atom is called its electronic configuration. Let's dive in and learn about the direct connection between the electronic configuration of the elements and the periodic table. We already know that in the periodic table there are 7 horizontal rows known as periods and 18 vertical columns known as groups. First, let's discuss the electronic configuration in a period. The period indicates the value of n for the outermost or valence shell. In other words, successive periods in the periodic table are associated with the filling of next higher principal energy level. It can readily be seen that the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. For example, in the first period, the value of n is 1, which is the principal quantum number, and it has 2 elements. The first is hydrogen with electronic configuration 1s1, and second is helium with electronic configuration 1s2. Here, the first shell K is completed. In the second period, n is equal to 2. It starts with lithium with atomic number 3. Here, the third period enters the 2s orbital. The next element, beryllium, has 4 electrons and has the electronic configuration 1s2, 2s2. Starting from the next element, boron, the 2p orbitals are filled with electrons when the L shell is completed at neon with outer configuration of 2s2 and 2p6. Thus, there are 8 elements in the second period. On the other hand, for the third period, the value of n is 3. It begins at sodium and added electrons enters 3s orbital. Successive filling of 3s and 3p orbitals gives rise to the third period of 8 elements from sodium to argon. In the fourth period, the value of n is 4. It starts at potassium and the added electrons fills up the 4s orbital. Now, you may note that before the 4p orbital is filled, filling up of 3d orbitals becomes more energetically favorable, and we come across the so-called 3d transition series of elements. This starts from scandium with atomic number of 21, which has the outer electronic configuration 3d1, 4s2. The 3d orbitals are filled with zinc having atomic number of 30 with electronic configuration 3d10, 4s2. The fourth period ends at krypton with the filling of 4p orbitals. Although we have 18 elements in the fourth period, whereas the fifth period, the value of n is 5, beginning with rubidium and is similar to the fourth period and contains the 4d transition series starting at yttrium with atomic number 39. This period ends at xenon with the filling of 5p orbitals. The sixth period, where the value of n is equal to 6, it contains 32 elements and the successive electrons enter 6s, 4f, 5d and 6p orbitals in the order filling up of 4f orbitals. It begins with cerium having atomic number of 58 and ends at lutetium with atomic number of 71 to give the 4f inner transition series, which is also called lanthanoid series. In case of seventh period, where the value of n is 7 and it is very similar to the 6th period with the successive filling of the 7s, 5f, 6d and 7p orbitals. And it includes most of the man-made radioactive elements. This period will end at the element with atomic number of 118, which would belongs to the noble gas family. Filling up of 5f orbital is after actinium with atomic number of 89 gives the 5f inner transition series, which is also known as actinoid series. The 4f and 5f inner transition series of elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping elements with similar properties in a single column. Let's now discuss the group-wise electronic configuration of elements. All the elements belonging to the same group have similar electronic configuration. For example, group 1 elements or the alkali metal all have NS1 valence shell electronic configuration, whereas group 2 or alkaline earth metal have NS2 configuration. Group 13 or we can say boron family have electronic configuration of NP1 and so on. This classification is based on the type of atomic orbitals to which a differentiating, that is, the last electron enters. On the basis of the electronic configuration, the elements are grouped in 4 blocks, that is, S block, P block, D block and F block. Depending on the type of atomic orbitals that are being filled with electrons. There are 2 exceptions to this categorization. Helium belongs to group S, but its positioning is in P block along with the group 18 elements is justified because it has completely filled valence shell and exhibit the properties, characteristics of other noble gases. The other exception is hydrogen. It has 1 s electron and hence can be placed in group 1 alkali metal. It can also gain an electron to achieve a noble gas arrangement and hence it can behave similar to group 17. Because it is a special case, we shall place hydrogen separately at the top of the periodic table as shown here. Let's now discuss the salient features of 4 types of elements marked in the periodic table. Let's start with the S block. The elements of group 1, that is alkali metal, and group 2, that is alkaline earth metal, having NS1 and NS2 outer electronic configuration belongs to S block. The metallic character and the reactivity increases as we move down the group in the S block. Therefore, the elements are very reactive with low ionization enthalpy. And because of high reactivity, they are never found pure in nature. They readily lose electron to become stable. The compounds of the S block elements, with the exception of lithium and beryllium, are predominantly ionic. In case of P block elements, the differentiating electron enters the p orbital of outermost shell. This block includes group 13 to group 18 and are called representative elements or main group elements. The outer electronic configuration varies from Ns to Np1 to Ns to Np6 in each period. At the end of each period is a noble gas elements. All the orbitals in the valence shell of the noble gases are completely filled by electrons. The noble gases thus exhibits very low chemical reactivity. Elements of group 17, that is halogen, and group 16, that is chalcogens, readily add 1 or 2 electrons to attain the stable gas configuration. Thus, they have high negative electron gain enthalpy. If you see the non-metallic character across p block elements, it increases as we move from left to right across the period, and the metallic character increases as we move down the group. Let's now discuss the d block elements. This block includes element from group 3 to 12. In these elements, the differentiating electrons enters in n-1 d orbital, and the general outer configuration is n-1 d 1 to 10 ns 0 to 2. D block elements lies in between s and p block elements and are thus known as transition elements. However, zinc, cadmium and mercury do not show most of the properties of transition elements. D block elements are all metals. They mostly form colored ions, and it exhibits variable valency. And it also shows paramagnetism and often used as catalyst. On the other hand, in F block elements, all are metals, and the differentiating electron enters in n-2 f orbital, and the general outer electronic configuration is n-2 f 1 to 14, n-1 d 1 to 10, ns 0 to 2. Hence, it is also called inner transition elements or F block elements. There are two series of F block elements corresponding to the filling of 4f and 5f orbitals. One is the lanthanoid series and the other one is the actinoid series, as discussed earlier. The chemistry of actinoids is more complicated than the corresponding lanthanoids due to the large number of oxidation states shown by them. All the F block elements are metals. Actinoid elements are radioactive in nature. But do you know, many of the actinoid elements have been made only in nanogram quantities or even very less by nuclear reaction, and their chemistry is not fully studied. For such amazing update, stay tuned for our next upcoming video. Now let's summarize what we have learned.
Manorama Horizon. Learning made simple.